Hello, everybody, and welcome to this session. I'm Sergej Faletić from the University of Ljubljana, and I was asked to talk about quantum education. And I titled my talk, What do we want and how can we get there? Quantum physics is huge. We have the black body radiation, we have the photoelectric effect, we have the Bohr atomic model, we have the double slit experiment, we have the Stern-Gerlach experiment, we have the de Broglie model, we have the Schrödinger equation, we have the Heisenberg uncertainty principle, and we haven't even gotten yet to quantum field theory, to the ladder operators, to Feynman diagrams, and so many more. So out of all of this, what should we teach? And of course, one answer would be, at university level, we can teach it all. Okay, but still, we have to start somewhere. And so where should we start? One idea would be to start from the beginning, to go chronologically. To start with the black body radiation, which started it all, and then proceed through all the old physics of quanta, which is the term given to all the quantum elements of knowledge until 1925, and then beyond that. In fact, we can see that much of these topics are already covered in high school curricula. This is a research done by Kirsten Staderman, and it compared different curricula, and all these black dots mean the topics that are covered in the different curricula. And we can see that the old physics of quanta is basically covered by all curricula. So that's great. But the International Year of Quantum Physics and Technology is not about that. It's about the Schrödinger equation, which was developed in 1925. And that's why we have a 100-year anniversary. This equation has a meaning behind it. And so the next idea was, let's teach people how to read the meaning behind this. It turns out that the meaning behind this ends up with the description of particles, which is wave-like, and it includes complex numbers. We know from research that students have problems with waves, even in classical mechanics. Adding complex numbers to that does not help. These topics are covered in high school curricula. We see that the black dots are more sparse. They are not as well covered. But the Schrödinger equation itself, which is this emphasized line, is covered only by a few curricula. And that makes sense, because this is not easy to understand, and it requires a lot of mathematical knowledge beforehand. So maybe it's good for scientists and at the university level, but this only reaches a very small portion of the population. Whereas today, we are covered with the term quantum everywhere. We have quantum ice cream, quantum Snickers, quantum day cream, lots of them. And we even have quantum real estate. So none of this is really quantum. So maybe it would be time to teach students what really is quantum and what is not. So the next question was, can we explain the meaning behind this in a different way, in a simpler way? These two equations can lead us to this different way and can lead us to understanding some concepts of quantum mechanics in a different way. And by the end of this talk, you will be able to understand the meaning behind these two equations, at least to a degree. This brings us to two-state approaches. If we take a look at these equations, we see that they operate with something called states, up, down, left, right. We'll learn what this means. And there are many different two-state approaches. You can approach it through polarization, through spin, through which way, which is a Mach-Zehnder interferometer, through a double well experiment, even through quantum technologies. They all operate on two-state systems. And so all of these are viable options to introduce two-state systems. They all have a few things in common. They only cover about 4 or 5 key concepts. They do not have any waves. They have nothing or very little math. And at the end, students should be able, and in many cases are demonstrably able, to reason about quantum phenomena, at least on a basic level. So now we have another direction. A direction aimed at general education, at the general public, something that can be done in high schools. That's great. But even so, decision makers often ask, why is this necessary? Why should we forego some topics of classical physics in favor of quantum mechanics? Enter the second quantum revolution. In 2018, at least the European Union was very clear that they expect a necessity for the quantum workforce. And to produce quantum workforce, you need to start educating people that this is a possible career early enough. And so what they did, they launched a program. And within this program, they launched an education initiative, the QT-EDU, which then developed into the QCATS. And both initiatives are aimed at developing the necessary base for quantum technology workforce, sometimes called quantum engineers. And they sat together, and in years, they came up with so-called European Competence Framework for Quantum Technologies. You're welcome to scan the link and see it for yourself. What they did is they constructed 3 domains: concepts, technology, and economy. And within each of these domains, they determined 6 different proficiency levels. They determined the subtopics within each domain and the criteria for the proficiency levels for each domain. And we can see that there is some overlap between concepts. Some fall under one domain and maybe more than one domain. And this triangle in the middle is supposed to represent quantum literacy. These are the topics that everybody should know in order to be able to reason about quantum technologies. This is not just about quantum mechanics. It's also about the viability of quantum technologies, the economy of quantum technologies. That's why it covers all 3 domains. And so now we have another avenue, the avenue of quantum engineers. And this is also aimed at electrical engineers and maybe even mechanical engineers, computer engineers. And so maybe it does not need to cover that many basic quantum topics, or let's say more physical quantum topics, and more geared towards engineering topics. In the meantime, GREP, the International Group on Physics Teaching, also developed their own initiative, the GREP community. It got together 46 experts from 21 countries, and they discussed many different questions. They met in different years, discussed different questions, and among those questions were also, what should we teach? What are the core concepts? What are the currently existing approaches to teach it? So how to teach it? And so what did we get? Let's compare the findings from both of these initiatives, from the Quantum Technology Framework and from the GREP community first. We can see that there are 5 topics that both the GREP community and the Quantum Technology Framework agree are very necessary for quantum education. Interestingly, the existing curricula does not cover all of these topics, or it just covers them partially. on the other hand, we have topics that are very well covered by the existing curricula, but deemed unnecessary by the GREB community and the quantum technology framework. Why is this? Because most of the existing curricula are still based on the wave-like quantum mechanics, which we are celebrating this year. But this quantum mechanics is not very relevant for current quantum technologies and for understanding the fundamentals of quantum. And so the existing curricula, which have been developed years ago, are lagging a little behind the current necessity or desires expressed by the communities and the experts. And I also want to point out these philosophical implications of quantum mechanics, because we will return to that. And we can see that the GREB community consider this important. The quantum technology framework did not touch it, and the curricula only partially covers it. So now we have three avenues, which vaguely correspond to three educational levels or programs. And all of them agree on 5 core concepts. Now that's great. These 5 core concepts cover much of this internal triangle of quantum literacy, but they do not cover the economy of quantum technologies, because this is something that may change, while the core concepts do not change, and the fundamentals of the quantum technology also do not change. So these are the parts that are well covered by these 5 topics, whereas the economy, not that much, or not at all. So how to teach these 5 concepts? One way would be to say, okay, let's just get students together and tell them what they need to know. The problem is that this works for about 20% of students. To understand why this is, we must understand how learning works. I like this particular sketch. You can see it on this cat, which has nothing to do with physics. We start with concrete experience. The cat observes that the bag smells nice. Then it integrates this knowledge into its pre-existing knowledge. She has previously identified patterns that when the bag smells nice, she gets treats. So she says, okay, the bag smells nice, maybe there are treats in it. Then she conceptualizes this in a plan of action. So what can I do about it? Now, if my hypothesis is correct, that the bag contains treats, then maybe I can go and find those treats. And then she acts and goes and in fact finds the treats. And by repeating this cycle many times, we learn the patterns and then use these patterns to identify, when we observe new observations, we use these patterns to sort these observations and to put them in the right place and to decide actions based on that. Now, this is a cycle, and this repetition of this cycle to identify patterns and to accept these patterns is very important. When we teach students and we just tell them what they need to know, we are providing this concrete experience. We are telling them, and students are listening. But other than that, students aren't doing much. Even if we explain the reasoning, students are still just listening to our reasoning. They are not asked to do the reasoning. So all the other parts of this cycle, they have to do at home. And about 20% of students are very efficient at this. Maybe they have the right circumstances at home. Maybe they have the right motivation. Maybe there can be many factors. And for about 20% of students, this works well. For the rest of the students, they may not have the correct environment to do this. So maybe they have a family at home. Maybe they cannot put as much time into this. Maybe they're in high school, maybe they're just not that interested. Maybe they do not have a supportive environment at home. Maybe they have to do some other stuff and don't have time to study at all. And so all this part of the cycle remains untouched. And so their learning is not as efficient. But even for those 20% for which the learning is efficient, this is a sentence that stuck with me. And it's a title, part of the title of an article. The problem is not understanding the theory, but accepting it. So even if they come and understand the theory and they produce all these necessary cycles, they still have trouble accepting it. Why is that? Well, the problem is this link to concrete experience. We don't have any concrete experience in quantum physics. So what can we do about it? This is not just something that we can provide. We don't live in a quantum world. So what can we do about it? One way is to do games. Games are a way in which students can learn new rules without connecting them necessarily to the existing pre-knowledge. When we learn bridge, we don't ask in what way this connects to the real life. Same with chess. We don't ask how this connects to the real life. We don't expect a connection. And in the same way, people have designed games like quantum tic-tac-toe, quantum cryptography, and quantum moves, and there are many others. And these are all games that can be played for students to familiarize themselves with the concepts of quantum mechanics, with the rules. The idea is that when they eventually learn proper quantum mechanics, they will have something to connect this quantum mechanics to. So far, we don't have enough evidence of how much this works, because games are mainly used not in school, but in outreach. And in outreach, it is very difficult to gauge student understanding. So we are in the middle of research of how well games actually accomplish this goal. We know that students can learn the rules, but we are not sure yet how well this then translates to learning quantum physics. Another thing would be to exploit the nature of science. We can see here below that the nature of science is basically covered in all curricula, but the dots are white. These white dots indicate that these topics are covered, but they are not tested explicitly. So nobody ever asks students the nature of science, the processes that scientists use when they come to their knowledge. By using the nature of science in quantum physics, we can also provide then this formative assessment of how well students have learned nature of science, of at least how well they can use it. The scientific process, the nature of science, works very similar to the natural learning process. We start with concrete experience, with an observation. Then we do some more systematic observations to find patterns. Based on these patterns, we propose hypotheses, how relations between quantities are, and what could be the connections between them. And then we propose some testing experiments to test our hypothesis. We predict the outcomes of these experiments. If our hypothesis is correct, then what should happen in this particular experiment? We perform the experiments, we observe the outcomes of the experiments, then we compare the prediction with the outcomes, and we make judgments about the hypothesis. If they match, then we are happy. We can proceed and do something applicative with our new hypothesis that apparently works. And if it doesn't, then we have to revise the hypothesis. Maybe we made wrong assumptions. Maybe we need to add something to the hypothesis. We perform more experiments, and so on and so on. The difference between this and the natural learning process is that we do not necessarily need the connection to the concrete experience. We can identify patterns that we have not seen before and base our hypothesis and our testing on these patterns. So, how can we teach quantum physics, exploiting this nature of science that I just explained? Let us start with a system, a particle, and this particle has a property. This property can be represented by a vector, and this vector can be oriented in any direction perpendicular to the direction of motion. We will denote these directions by up, down, left, and right. And this black vector that you can see can be oriented in any of these directions. Then we have a device, which is this blue box that you see. And we can orient this device also in any direction we want. So you can direct up, down, or left, right, or in any other direction that we want. The device is designed so that if the particle has the property up, directly up, this vector directly up, then it should come out of the device at the top. And we will denote this up, like the uppermost possible exit. If it's oriented down, the vector is oriented down, then it should come out of the device at the bottom. That's in the most down position. So we will denote this down. If the vector is oriented left, then it should come out in the middle, because it's neither up nor down, and the device is designed such that this should come out in the middle. Same for the right. And if it's oriented anywhere in between left and up, or left and down, or right and up, right and down, it should come up somewhere between the middle and up, or between the middle and down. Okay. So now we go and we perform this experiment, and we see that that's not what happens. Instead, we only get up or down. We never get anything in between. So no matter how the vector is oriented, we always get the result either up or down. And there is a statistics between up and down. If the vector is oriented up, we always get up 100% of the time. If it's oriented down, we always get down 100% of the time. If it's oriented left, then we get up and down 50-50. Same for right. And if it's oriented somewhere in between, then the percentages of up and down are adjusted according to this. So the more up it is, the bigger percentage for up and the lower percentage for down. And the more down it is, the bigger percentage for down and the smaller percentage for up. We thus came to the first finding in quantum physics, which is we have only two possible results. It's either up or down. It's nothing in between. This was an observation. This was the observational part of the nature of science. Now, we have already identified several patterns. A vector up will always give us up, a vector down will always give us down, a vector left will always give us 50-50, and the vector right will always give us 50-50. We can identify these same patterns if we orient the apparatus in a different direction. So if oriented left-right, instead of up-down, then we get similar results. Left will always show left, a vector right will always show right, a vector up will now show 50-50, and the vector down will now show 50-50. The next concept is indeterminism. So we have observed here that we have certain patterns, but we have these 50-50 splits sometimes in certain occasions. And these are not exactly 50-50 split. So if we repeat this experiment many, many times, we will see that this split is 52, 48, or 54, 46. It's not always 50-50. It's about 50 plus minus 7 in each direction. So this already indicates that there might not be a pattern of how this left-right or up-down occur. And we can log these individual results, we just one by one, and see if there is a pattern in it, if it's always up, down, or up, down, up, down, or something similar. And we now ask students to identify this pattern, and students can't identify a pattern because there is none. So we came to the second finding of quantum mechanics and the second concept, which is indeterminism. We cannot predict for single experiments, we cannot predict the outcome. If there is a chance for both outcomes, then we cannot be sure which of the two will occur. But we can be sure about the statistics, so it will be 50-50. But we don't know for one specific outcome which one it will be. So now it's time to build some models based on this. And we will introduce the concept of states. Now we have talked about property, which is this orientation of the vector. And now we will introduce a state. The state is denoted with this funny looking bracket. For now, it doesn't matter what exactly it means. It has no particular meaning except that it lets us know that this is a state and not the property itself, but the state of the system. And so we say that the system is in the state up if it always shows the result up. We say that it's in the state down if it always shows the result down. Likewise, we say that it's in the state left if it always shows the result left. And it's in the state right if it always shows the result right. How about these situations? Well, the preparation of the particle is the same. The orientation, the initial orientation of the vector is the same as in the states that we have discussed so far. So it would be logical to give them the same names. And we can see that the state left, here in the top right most corner, the state left, if we measure it up-down, we will get 50 up, 50 down. Likewise for the state right, and for state up, we will have 50-50 left-right, and 50-50, and for the state down, we will have 50-50 left-right. So we see another pattern. There is no way to have 100% certainty about both directions, about up-down and left-right. There is no state in which we can say for sure that it will be up and left. If we know that it's up, then left-right will be 50-50. If we know that it's left, then up-down will be 50-50. And this is called the uncertainty principle. And we have discovered the third concept of quantum mechanics. Students then start asking themselves, well, if the state left in the measurement up-down results in 50-50, is it possible that it's composed of 50 particles, so of half of the particles in state up and half of the particles in state down? Could we interpret the state left in this way? And this is a valid hypothesis. So, according to the scientific process, we now propose this hypothesis and we proceed to test it. Let's first check if it fits with the observations so far. And we see that it does. If we have 50% of up, they will show all up. If we have 50% of down, they will all show down. And we will have in the result 50 up and 50 down, just like we really have. So now let's propose a testing experiment. In our experience, it is best if the instructor proposes this experiment because there are many possible experiments and students do not yet know enough about quantum mechanics to be able to propose productive experiments. So we propose this experiment. We measure left-right. And let's see. On the right-hand side, we have our hypothesis, and now we have to make the prediction for this particular testing experiment. If we have 50 particles in state up, what should the result left-right be? How about for the 50 in the state down? I will give you a few seconds to think about it. Well, the reasoning should go something like this. State up, if measured left-right, shows 50-50, and we have 50% of these particles, so we should get 25%, 25%. And the same for state down. So altogether, if we have 100 particles in state left, and these can be, in fact, thought of as 50 in state up and 50 in state down, we should get 50-50 split for this state, for this experiment. Let's perform the experiment, and the actual result is 100 left. This is not a surprise because this is one of the patterns that we have already observed. So now it's time to judge our hypothesis. Is our hypothesis valid? Oh, we have to reject it because the prediction based on the hypothesis did not give the did not match the actual outcome. Okay, so this is one very important finding, which is that a state which seems to be a combination, for example, a state left, which seems to be a combination of up and down, cannot be thought of as half of the particles up and half of the particles down. It's a different kind of combination. Now, what kind exactly? That's up for debate. One might say it's like in both states at the same time. Maybe. Maybe it's in neither of the states and it just becomes in a state when measured. Maybe. We don't know. And until we have a way to test these different interpretations, there is no point in discussing them. Students may have one or the other of the interpretations, but we cannot differentiate between them. All of them are valid. And this is why some of the experts refuse to engage in these philosophical implications of quantum mechanics. So what does this mean? Can a particle be in two places at the same time? Can the Schrödinger's cat be dead and alive at the same time? We don't know what it means. We don't know how to interpret this. We can imagine, but anything we imagine goes unless we have a way to test any specific interpretation. And so far, we don't. So we call this situation a superposition, and I promise that you would be able to read at least one of those equations. And here you have exactly one of the equations that I showed in the beginning. Okay, so what's next? There's only one concept remaining. This was the fourth concept, and the next concept is the effect of measurement. So what does measurement do on the system? We again engage the nature of science, the scientific process. We prepare the particle with the arrow pointing to the left. We measure up-down, and then after, let's say we get the measurement up, we ignore all downs, we just get one up result. What would be the state of the system after this measurement? We can ask the students this, and the students can propose hypotheses. And there are always three hypotheses that emerge. I've done this with many cohorts, and these three hypotheses always emerge. First is, if we have measured up, the state will be down. The reasoning behind this is that we expect a 50-50 split between up and down. And so if we have measured up, the next measurement should be down. And that makes sense. So very valid. The second hypothesis is that it will remain as it was before. So if it was left, we have measured something, we have gotten information out of it, but that's it. The state is still the same. It makes sense. This is how measurement behaves in classical physics. Third hypothesis is that it will be up. We have measured up, and so the state will be up. And there are a few more hypotheses that can emerge. They emerge very rarely, but they are also the only other possible hypothesis, and so I will include them here for completeness. Now we have hypothesis, we can propose testing experiment. The testing experiment will be, let's measure again up and down. What should happen if each of the hypotheses is correct? Students are now asked to make predictions, and we can do it with them. So I will leave you again a few moments to think about it. So what should happen for hypothesis 1? Well, hypothesis 1 says that the state will be down, and if we measure up down, we should expect 100% down. How about hypothesis 2? It says the state should be left, and so measuring up down, we expect 50-50. And the same for hypothesis 4, which is right. Hypothesis 3, it says up, and measuring up down, we would expect 100% up. How about the last one? Well, this is up to the students. They have proposed it, and sometimes they are not very able to articulate what exactly they mean by their hypothesis. And when they make a prediction, they can concretize their own hypothesis and say, okay, if my hypothesis is correct, then this should happen. And if it turns out that this is actually consistent with the real outcome, then fine, we can discuss it further. But if it's not, then we will have to reject the hypothesis anyway, and so it doesn't matter. Time to do the measurement, we get up 100%. Time to do the judgment about the hypothesis, and we have to reject all the hypotheses except one, usually. Usually, if the fifth hypothesis predicts the same outcome, then it's probably the same as the third hypothesis, probably. But this is very rare. I have not encountered this situation yet. So we have learned the fifth concept, which is the measurement gives the property to the particle. So the particle had some property before, and then we did the measurement, and afterwards it has a different property. And when we discussed whether it has a property up or down beforehand, we saw that we cannot really agree whether it did or not. So maybe it did, maybe it didn't, but we know that it has it afterwards. And in this particular case, we know that it did not have it before. So this can be interpreted as the measurement giving the property to the particle. In the same time, it changes the state of the system to the state that is consistent with having that property. So if it has the property up, the state will be up. Okay, now we have covered all the 5 concepts of quantum mechanics. Good for us. Now what? We have talked about what to teach, and we have narrowed it down to 5 fundamental concepts that all experts agree should be taught. We have discussed how to teach it. I only presented one possible way, of course, but there's only there's only so much time here, and there are many similar approaches that can be used to teach the same concepts. So we have achieved a level of quantum literacy. We have also gotten maybe empowerment of the quantum workforce, giving the students the opportunity to choose a quantum career, to know about it beforehand. But for me, the most important thing is we have taught the students how to think creatively, how to address problems that have not been addressed yet, how to come up with solutions that have not been found yet. And for me, this is the most important thing, especially in this time when we have artificial intelligence that can come up with everything that we already know, it is particularly important for humans to come up with the things that we don't yet know. So, and this is the way to, and now students have gone through this process at least once. They have experienced in what way new innovative ideas can be produced and tested. And hopefully they can use all this knowledge and these innovative ideas to create a better future for us all. Thank you very much.
We have some time for questions. I loved your quote about the AI, by the way. So questions? Do we have? Okay.
Thank you. So this has to do with the probability interpretation of quantum mechanics. And we know from Newton it's deterministic. So I'm sure a lot more people would want to know, will the probability interpretation affect the calculations that we do in quantum?
Did you hear that, Sergey?
Yeah, I think I did. It was about the probabilistic interpretation of quantum mechanics and how it affects our calculations, right?
Yeah.
Yeah. So I don't feel comfortable answering this question directly because I think these are very subtle things that experts who are very deep into the quantum world and who are testing like Bell inequalities and are testing the teleportation mechanisms, they find this kind of subtle nuances between the different interpretations, but so far it all comes back to the same calculations. Independent of how we interpret, whether it's probabilistic or many worlds or whatever other interpretation we have, even the hidden variables, non-local hidden variables interpretations, they still use the same mathematics and they still kind of get to the same results. The moment one of these interpretations will not get to the same results as any other, then we will know either that this is not the correct one or that this is the correct one. And as far as I'm aware, it has not happened yet.
Okay, thank you. Another question here in the room? Anybody? Do we have online questions? Okay.
We have a hand up on Zoom.
Okay. I can't see them, but maybe you can, Sergey. Oh, okay.
Hello.
There's one.
Good morning to you, to all. Can you hear me?
Yes, I hear you. I do.
Yeah,
we do too.
Sergej, thanks. First of all, thanks for your interesting speech. I'm a social scientist and system thinker, but I think that beyond the traditional logics of separation, confinement of knowledge and skills, there are a lot of possibilities to not only to sharing ideas, knowledge, and project them, also to share the epistemology and methodology of knowledge, because as you know very well, we have two fundamental problems beyond the scientific sector, the separation of scientific sector. What is knowledge, and what are the methods to achieve knowledge? So my question is, I totally agree about the urgency of try to educate into creative thinking. What is your opinion about the risk of produce, sorry for the verb that is not human beings, the risk of produce only young students, young scholars with only technical and hyper-specialistic preparation?
Interesting question. Thank you.
Yeah.
Yeah. So I separate. So to me, this. So I do mostly work. I mostly work with high school and with physics teachers, and for that population, I think that is the time to broaden the perspectives of, like you said, epistemology and even different epistemologies. So epistemology means how we know what we know. And this is different for different topics. So for physics, it's one way. For chemistry, it's a different way. For history, it's a third way. And instead of learning just the knowledge that we have gained, I think we should learn how we got to that knowledge. And that for all particular subjects, for history, for geography, for physics, for everything. Because this is the important thing. When people are asked to judge whether something is reasonable or not, they need to know how people create this kind of knowledge. And so to me, that is the time to do this. But as the technologies progress and they become more and more specialized, I think university level, or at least the second part of the university level, is when specialization should start occurring. And I can see this in many faculties, that you are a general physicist, but when you're asked about, I don't know, quantum optics, even people who do introductory quantum mechanics don't know quantum optics enough to answer specific questions, because they are focused on, I don't know, solid state physics or something like that. And so these kind of specializations must occur at some point, because the technologies are too specific to be accessible by a very broad mind. But until then should be the time to broaden the spectrum. That's my opinion on this, if I understood correctly your question.
Okay, do we have another? I have one here in the room.
Thank you very much. Please, in the course of the presentation, you mentioned discussing the fifth concept that was on measurement, and you asked what then will be the state of the particle after the measurement. I would please like a bit of clarification on that, looking at the concept of superposition. So now that we are done measuring the state of the particle and it's no longer under measurement, does it not rather exist in its left or right or up and down state? Or after the measurement, it now has a very specific state that we can make further analysis on? A bit of clarity on that, please.
Okay, I hope I understood the last part of the question correctly, but the first part was about the state after the measurement. From what we understand from the process of measurement, the state after the measurement is the eigenstate that corresponds to the measured value. We will always get one of the eigenvalues possible in the measurement, and the state immediately afterwards will be the eigenstate corresponding to that value. However, this state may evolve in time, and it may become something different if we leave it long enough. That depends on the system. Some systems evolve and some systems are stationary. But the second part of the question was a little bit less clear to me. About the superposition state, I'm not entirely sure what exactly you're asking. Technically, I would just say this, technically the superposition state can be interpreted in a vector space. So you can make vectors, and I have a picture of that. I'm not sure if screen sharing will work, but I can try to share the screen just to answer this question. Maybe if this screen sharing works. Let me just find the right slide now. Yeah, because so this on the right hand side, I hope it's visible. You have vector spaces where you can interpret superpositions and eigenstates very clearly, and that's of course an advanced level of mathematics. you can do it in high school, but it's not necessary. And basically, from what I understand, people who do quantum physics mostly operate by thinking in these vector spaces. It's either this, or it's block sphere, or it's some sort of this kind of interpretation. And they don't often ask what this means in the sense of reality, because it might be outside what we have experience with. So it might be something that necessitates an abstract view that we cannot concretize very well in the things that we already know. Some people even say that we might not have the language developed to discuss quantum concepts, because in the nature of language, we just don't encounter this kind of concepts, and we did not develop language to describe this kind of situations. So I don't know if this answers the question. I hope it does, but if it doesn't, I'm happy to elaborate more.
Okay. Thanks a lot, Sergej. I think we're running out of time now, so I'd like to thank Sergej again for a wonderful talk.
Thank you very much.